This lecture is going to introduce maximum likelihood estimation, which is one of the most important methods of estimation in statistics. So we were talking about logistic regression last time, and we noted a couple problems that would prevent us from using least squares to estimate a logistic regression. So I drew this graph on the board last time around. There were a number of violations of the linear model. So we had a dependent variable that only took values 0 and 1, and we just had a single x variable that's continuous, and we want to be able to model the probability of y for x. Now, we talked about three problems. One is if we just throw a line up, the line goes out of bounds. So we dealt with that last time by taking the logit function. Instead of modeling y, we're going to model the log odds of the probability of getting a 1. And so that enables us to avoid going out of bounds. I mentioned two other problems, though, and the two other problems are not going to be so easy to address. So the first was our residuals will always take only two values. So for a given x, I'm either going to observe a 1 or I'll observe a 0, and I'm going to guess some probability in the middle, which means I have two possible values of my residuals, which are Bernoulli trials, so they're not normally distributed. Another problem is that if you remember, the variance of a Bernoulli trial is just pi times 1 minus pi, and so what that implies is that we have heteroscedasticity. So if you think about the graph of pi times 1 minus pi versus n, it's going to be a parabola, and so it's going to achieve a maximum value when pi is 0.5. All right, so we got heteroscedasticity, we have non-normal residuals. How are we going to handle that? The answer is maximum likelihood. So I want to give you a sense for what maximum likelihood does, and also teach you some of the vernacular that you'll see in logistic regression output and the output of many other procedures. So what exactly do we mean by a likelihood? What's negative 2 log likelihood? What's deviance? Those are the sorts of questions we'll answer in this lecture. All right, let's start with a real simple problem. So let's say I have a random sample of size 5 from some population, and I send this random sample some offer and wait for people to respond, and lo and behold, 2 out of the 5 respond. So the question is, what is our best guess of the response probability? So there's really some parameter that we're trying to estimate. The parameter is pi, the probability of a head, or a response in this case. So what's our best guess as to the probability of pi, or I guess I called it p here? Well, back in your first stats class, or probably before your first stats class, you would have just said 40%. And your rationale would be, well, 2 out of 5 respond, so 40% is my best guess. We're going to develop a more useful rationale for that with maximum likelihood. So this is the rationale. It's a subtle idea, but very important. So the subtle idea is this: we're going to pick our estimate of pi, so that we make the probability of observing the data that we have on hand. So we've observed 2 responses out of 5 tries. We want that probability to be as large as possible. Okay, so make the likelihood that we're going to observe 2 responses out of 5 tries as large as possible by picking pi. Now, if you think about it, a large value of pi, like 0.9, would imply that 2 responses out of 5 tries is not very likely. If pi really were 0.9, we'd expect more like 4 or 5 responses out of 5 tries. All right, so let's do this. the first thing that we always have to do is to write out the likelihood of observing the data that we have as a function of the unknown parameter. Now, let's do this with what we learned in basic probability theory. So what we really have here is a binomial distribution. So binomial distributions flip a coin some fixed number of times, in this case 5, and it tells us the probability of observing a certain number of heads, in this case 2. So the likelihood, which we're always going to denote by a big L, so big L at our parameter, is just going to be a binomial. So 5 choose 2, that's the number of ways we can get 2 successes out of 5 tries. Probability of success raised to the number of successes, probability of a failure or non-response raised to the number of failures. Now, in this case, it wouldn't be too difficult to maximize the likelihood directly, but instead what we're going to do is take the log of it. So the log is a monotonic transformation, and it's going to make it easier. So we want to avoid, to maximize this, we'd have to use the product rule, and that would be kind of hard. I mean, it wouldn't be impossible here. In subsequent examples, we'll see we don't want to be taking derivatives of products. So when we take the log, we turn those products into sums. So let's do that. Now notice the value where the maximum is achieved doesn't change at all. The only thing that changes is we don't have to take derivatives of products. Okay, so what's the derivative? What's the log of this mess? Well, since we have a product, we can just add them up. So we have log of 10, that's 5 choose 2, plus, okay, we take the log of that second term, the exponent comes in front, so 2 times the log of pi plus 3 times the log of 1 minus pi. Now we need to find the value where this is maximized. So let's take the derivative. Here's the derivative, you solve it. Lo and behold, you get 2/5. So let me just repeat what this has told us. If we assume that the unknown parameter is 0.4 or 2/5, we maximize the likelihood of observing the data that we have on hand. So 2 responses out of 5 tries. I made a little table where I just generated these probabilities. I took the likelihood and the -2 log likelihood, and you'll see if we'd chosen a pi of 0.35, it wouldn't be quite as likely. We wouldn't have observed the data we have so much as if we pick 0.4. All right, so that's the idea of maximum likelihood. Let's look at another example, and let's keep this kind of simple. Hopefully through these examples you'll see how this generalizes to larger samples. But let's say I have a random sample of size 3 from a population that I know is normal. Problem is, I don't know the mean. So I guess I'm drawing this sample in order to make a guess as to what the mean is. Now, somehow I do know the variance, and so the variance is 5. The sample I've drawn is made up of 3 values, so 4, 5, and 6 are the 3 values I've observed. What is the best guess of mu? Well, the basic stats answer would be add them up, divide by 3, and I guess the rationale for that's common sense. Actually, this is another method of estimation called the method of moments, which you'll study in another stats class, but that's the more formal rationale for using X bar. But let's try to do this with maximum likelihood estimation. So remember what maximum likelihood says. We want to pick the unknown parameter. In this case, the only unknown parameter is mu, so that the likelihood of observing the 3 values is as large as possible. All right, so recall that the PDF of a normal distribution, so we've been told this thing is normal, the PDF is this expression. Now, we need to start by writing the likelihood for the data. So since our observations are independent of one another, I'm going to multiply. So, we're going to multiply this PDF 3 times, substituting in different values of xi. So the only difference between this PDF and this likelihood is I now have an xi and I'm going to take the product. So we could think of this thing where we substitute 4 in, times this thing when I substitute 5 in, times this thing when I substitute 6 in. Now you can see why we want to avoid taking derivatives of products, because that would be fairly messy. So to avoid that, we take the log. We always use little l for the log likelihood. So this is called the log likelihood. And so this becomes a sum. And this expression, we can think of 2 pi sigma squared as really having an exponent of negative 1/2. So think of this as minus 1/2 times the log of that quantity. And then we take the log of an exponent. The exponent just goes away. So this is just negative this quantity. Now if we look at this closely, what we really have is the sum of 3 of these things. And this is just a constant. So let's just say K1. So that's the sum of those 3 things. And then what we have is some other constant times this quantity. So xi minus mu squared, which looks a lot like least squares. In fact, that's exactly what it is. We're trying to find, it turns out that x bar is also the least squares estimator of mu. The maximum likelihood and the least squares estimator in this case are exactly the same. Okay, so anyway, we have to minimize this. What happens? Well, K1 goes away when we take the derivative, and then we're left with this K2, but if we divide both sides by K2 after we set this equal to 0, K2 goes away. So in essence, we have to pick our value to minimize this quantity. So in other words, we're going to choose mu to be 1/3 times the sum of the x's, which is what we got using common sense. All right, so that's maximum likelihood. Let's now do maximum likelihood for logistic regression. So for logistic regression, again, the assumptions are, we're going to do simple linear regression in this example. We have observed pairs, so xi and y sub I. The only thing that's different from simple linear regression is that y sub I has to be a 0 or a 1. Now we're going to let pi I be the chance that observation I is a yes. And then last time we saw how the logit of pi over 1 minus pi was going to be modeled as some linear predictor. So alpha plus beta xi. Now let's write out the probability for a single person. So the probability that we observe some value y for person I is just going to be whatever this person's probability of a yes is, raised to the y, 1 minus pi, 1 minus y. Okay, so in other words, what is f at 1? Well, f at 1 would be pi. What is the probability that we get a 0? So what is the probability that person I says no? Well, this term turns to 1, and then this term is 1 minus pi to the 1. So the answer is the probability that someone is a 0 is 1 minus pi. Now, since our observations are independent, the probability, the likelihood is just going to be the product of all these things. So we're going to multiply across, and my goodness, this product goes all the way up to n, so we don't want to try to take logs in this case, derivatives of these products in this case. So let's go log it. Now, the algebra here is straightforward. So if we take the log of this expression, the product turns into a sum. The yi comes down in front, and we just have the log of pi. And then the same thing happens here. So the exponent comes out in front. We have the log of 1 minus pi. Now we have to do a little bit of math. We know we can solve this expression for pi and drop that in. We do some simplification, and we get this expression. So I'll leave that as an exercise to you all. And so again, you just have to play with this expression up here and substitute it in, and you'll get this. Now the point with this expression is that it's a function of only my data. So my data is these y's and x's, and the unknowns. So the unknowns are alpha and beta. Okay, so we need to maximize this. Just for kind of completeness sake, I thought I'd show you how we could do this in Excel. Let's go back to the bottle problem. So remember the bottle problem. The bottle problem was we had 6 different deposits that we put on a bottle. We issued 500 bottles, or we sold 500 bottles with a deposit of 2 cents. We sold 500 bottles with a deposit of 30 cents. We observed y, the number that came back. So that's what I've called here. So notice my dependent variable is really, maybe I shouldn't have called this y. I should have called that the number of returns. But my dependent variable is a 0, 1. Either they return it or they don't. Now we estimated a logistic regression in R last time. So we regressed y on x, and we said this was a binomial, and this is the equation that we got. Okay, what I thought would be an interesting exercise would be to try to implement this likelihood in Excel. So let's go do that. I typed the data into Excel. All right. Let's call this a plus bx. Now we should define our parameters, so a and b. So a is going to be the intercept, and b is going to be my estimate of beta, the slope. And I'm just going to take some guess. Let's call it 0.1 and 0.1. I have to have some starting values for this. Now let's go create this a plus bx, because notice that appears twice in the expression. So this is going to be $1 plus $2 times my deposit amount. So that's deposit. All right, now we can just copy this down. Let's now define the log likelihood, so L at pi. So this first term is just going to be the number of yeses. So think of that as, there are 72 yeses. So let's say B4 times my linear predictor. Now we're going to subtract off. Okay, the second term is the sum from 1 to n. So in other words, this is going to be 500 times. So 500 being that n value. So it's going to be 500 times. Now in Excel, the log function, the natural log function is ln. And this is going to be 1 plus the exponent of my linear predictor. All right. Now let's copy this down. And so the total log likelihood for my entire data set is going to be the sum of all these. So the sum of, what is that, E4 through E9. Now we can use Solver. So I'm going to go up to Tools, Solver. And we want to maximize the value of E10. So make E10, that's this cell, as large as possible by changing, let's see, we want to change B1 and B2. So B1 colon B2. There's no need to have the variables non-negative, so let's uncheck that box. Make sure that the method is this nonlinear optimization routine. Go hit solve. And a minute later, Excel comes back. Now let's just go compare what we got in R with what we got in Excel. So notice the intercept in R was minus 2.07, so it looks like that's right. The slope we also got right. And where's this minus 1503? Well, this 1503 is the likelihood. If we take minus 2 times that, we get something called the deviance. See, I think I just undid that, so I think we're going to need to redo the solver. I didn't mean to do that. All right, so deviance. So the deviance is going to be minus 2 times the log likelihood. So that's 3062.7. And so what you'll see is in R, that value is reported right here. And that's kind of like, I like to think of this as something like SSE. So it's the amount of explaining that hasn't been done by this model. So notice, the higher the likelihood, the lower the deviance. So the lower the likelihood, the higher the deviance. So it's kind of like how much hasn't been explained. There's a function in R called deviance that then returns that value for this fitted object. It's a very important part of this. So let's see, where is deviance? Fit $deviance is another way to get this. So it's just that is the objective function value, if you will. All right, so that's it for logistic regression. In another video, we'll come back and talk about a little bit more of how we use these deviance values.